the concept that we are about to discuss is Michaelis-Menten equation derivation. Okay, so how this equation came into existence, and basically the Km and Vmax relation came from this equation. Okay, so Michaelis-Menten equation provides a quantitative relationship between the substrate concentration and the rate of the reaction. Okay, so quantitative relation between the substrate concentration and the rate of the reaction. So let's see, before actually discussing the details, let's look at the concept itself. Oh yeah, yeah. Okay. Now, just pay attention. We'll be talking about the scenario. Whenever you do the experiment, or generally even in the nature, okay, so let's say you are eating rice, okay, and this rice basically has starch. The starch is reaching your stomach, or when you place it in your mouth, or so even in the mouth you have salivary amylase. So if you're taking a handful of rice and putting it in your mouth, the amount of enzyme when compared to the amount of starch that is there in the rice is very negligible, very negligible. Okay, so that negligible amount of enzyme, or when the carbohydrate finally reaches the intestine, even there the amount of enzyme that is released is very negligible. Even when you do your experiments in your lab, if you are taking 10 ml of a substrate, I'm giving you an example. If you take 10 ml of a substrate, you just have to add 0.1 or even less than 0.1 ml or less than that of the enzyme. Okay, so it depends on the efficiency of the enzyme, but usually the substrate concentration is always high when compared to the enzyme, very high. The substrate concentration is never the limiting factor. Whether you take in the biological systems, the example that I just gave you, you're taking rice. So the amount of enzyme that is acting on the rice, whether it is in your mouth or whether when it reaches the intestine, is very, very, very negligible when compared to the amount of the substrate. So it's important to understand that the substrate concentration will always remain high when compared to the enzyme. Okay. Now, let's say you wanted to buy something from the market. What do? You take your money and you go to market. So you're going with an empty bag first, and you're going to the market. And what do? You start buying more and more. So your bag starts to fill. Okay, so your pocket starts to lose. Okay, your pocket will become empty, but your bag starts to fill. Okay, that's exactly the analogy that we can apply for the enzymes. So when the reaction starts, you have this is the concentration. Okay, just focus on this. When the reaction starts, you have very high substrate concentration. Okay, so this is like the money that you have. Okay, this is like the money that you have. So the money, as the reaction proceeds, as you do more and more shopping, the money will go down to 0. Okay, so what is happening? The money is going down to 0, but the product, the red line, is increasing with the time. The substrate concentration is going down with time, but the product concentration is increasing with time. Okay, one is going down, the other one is increasing. Okay. And I told you that the enzyme concentration will always be negligible when compared to the substrate concentration. So you can see the enzyme concentration is somewhere here, the blue line. So initially what is happening? You have, let's say this is 100 units and let's say this is 30 units. You had 100 units of enzyme. It's not like that. It will be much negligible than that. But just for our discussion, let's say 100 and 30. Now what will happen, as this is in the start of the reaction, this is where it was. So you had enzyme 30, substrate 100. Now once you start the reaction, for instance, for the reaction to start, you need to keep the tubes at 50 degrees because the enzyme requires 50 degrees temperature for it to act, for instance. Okay, so you kept it at 50 degrees. So initially you start off the 30 enzyme molecules and you had 100 substrate molecules. Now, as the reaction proceeds, now that the temperature reaches 50, the enzyme will first combine with substrate. Okay, so what is happening to the free enzyme? Okay, you started with 30. Now the 30 enzymes are combining with, let's say, 30 substrate molecules. So the free enzyme concentration will continue to drop. The free enzyme concentration, the blue line, just focus on the blue line. The free enzyme concentration will continue to drop. At the same time, when the free enzyme concentration is continuing to drop, what is happening to the enzyme plus substrate concentration? The enzyme substrate concentration will continue to increase, the brown line. Okay, let me just erase everything and sorry. Now look at the lines again. Okay, so the black line is the substrate concentration, which is going down with time. The red line is the product concentration, which is going up with time. You started with certain enzyme concentration, which is much lower than substrate concentration, but even the enzyme concentration will go down with time because it is actually combining with the substrate to form the enzyme substrate complex. So the enzyme substrate complex will tend to increase with time. And towards the end of the reaction, when all the substrate is converted to product, you will no longer see the enzyme substrate complex. You will no longer see the enzyme substrate complex, and you will see the free enzyme coming back, original concentration. You started with 30, you have 30 enzyme molecules back. And you started with 0 enzyme substrate concentration, you will have enzyme substrate complex almost 0. Once the substrate is converted to product with time. Okay. So the Michaelis-Menten equation starts with two assumptions. The first one is it's a single substrate reaction and a single product is formed. The second assumption is, so let's say E plus S forward reaction, let's call it K1, the rate at which E and S are combining to form ES. Okay, K1 is the rate constant for E plus S combining to form ES, and they're also dissociating because equilibrium is maintained. Okay, the equilibrium is maintained. They're associating and then dissociating. So let's call this K2, right? And then let's call this K3. Okay, so the rate at which ES is dissociating to product. Okay, E plus P. So the rate at which E plus S are combining, you have the forward, and then this is dissociating. So the ES has basically two fates. It can go back to being E plus S, or it can move forward to being E plus product. But all the enzymatic reactions will involve an intermediate formation. Okay, this is the intermediate formation. And this intermediate, depending on the conditions, will move forward or it will go back to its original state. So here, in some cases, even this reaction is possible. In some enzymes, with some enzymes, even this reaction is possible, where EP is combining back to ES, even that's possible. The product can, so this reverse reaction is also possible. But in the case of Michaelis-Menten equation, that possibility is ruled out. There is no reverse reaction here. Unlike ES reversing back to E plus S, there is no reverse reaction in E plus P combining back to form ES. These are the two assumptions. First, single substrate is involved and single product is formed. That's the first assumption. The second assumption is the forward reaction from ES to E plus P is possible, but the reverse reaction is not happening. The reverse reaction is not happening. Now, assuming these two, they try to come up with a quantitative relation between the substrate concentration and the rate of reaction. Okay. Now, so what you have to understand here is when you do the experiment in the lab, which we discussed, what do? We take tubes, we add equal amounts of enzyme, and then we increase the substrate concentration. Okay, and then we get the free enzyme back and we get the product. We know how much product is formed. We can estimate it in the lab. You know how much enzyme you are adding. You know how much substrate you are adding. The only thing that you cannot determine is the concentration of ES. At any point, you won't be able to determine the concentration of the ES. Okay, you can't actually measure how much enzyme is actually bound to the substrate. So this cannot be determined. Okay, so we have to find a way, okay, to determine the effect of substrate or to determine a quantitative relation between the Vmax and the quantitative relation between the substrate concentration and the rate of the reaction. So you cannot measure this. So you have to work a way around. Okay. Now, let's see the Michaelis-Menten equation. Okay, so the first thing that we saw is enzyme plus substrate. This is your forward reaction K1, enzyme substrate complex. Okay, and then the reverse reaction is also possible, but here we are not seeing any reverse reaction. Okay, that's the second assumption. The first assumption is only one substrate, one product. Okay, and you're getting your enzyme plus product. So this is your rate of forward reaction. Okay, now the rate or the velocity, okay, is it for the product formation is K3 into ES. Okay, rate of formation of ES, the rate at which ES is formed is the rate K1 multiplied by the rate constant K1 multiplied by concentration of the enzyme and the concentration of the substrate. Now, it's not only forming, it's breaking down. So the rate of breakdown of ES is, it's breaking down in two ways. It can break down to form enzyme plus product, or it can break down to form enzyme plus substrate, because this reversible reaction is also possible. Okay, so you have to consider both the rate constants. So K2 and K3 multiplied by ES. Okay, now at steady state. Now this is where it becomes important. Michaelis-Menten equation is based on the steady state of the reaction. What is steady state? Now, the steady state, if you look at the steady state part of this reaction, so let me just make it a bit easier for you. The concentration of the enzyme, initially was somewhere here, right? And it is going down with time because it is combining with the substrate, and then it is coming back again. Okay, so it is coming back to its normal after converting all the substrate, let's say after 50 minutes, after converting all the substrate into product. Okay, there's no substrate to bind, so you're getting back your free enzyme. Okay, now what is happening to the ES complex? Initially the ES complex was 0. Okay, at time 0 the ES complex was 0, and with time it is increasing, and finally it is coming back. It is coming back. Okay, it is coming back to 0 again with time. Okay, and this won't go this long. Yeah, it's coming back to 0 again. There is a phase in between. There is a phase in between where you don't see a change in the With time, you are not seeing this is a flat line. With time, you see, this is a flat line. Okay, with time, so after 20 minutes, if you look at the concentration of ES, okay, let's say, just to give you a sense, let's say 10 units. After 30 minutes, what's the concentration of ES? Again, 10. Okay, and after 40 minutes, it's a straight line. After 40 minutes also, it's 10. Getting my point? So the concentration in this region, the concentration is remaining the same. So ds by dt in this period is equal to 0. There's no change. ds is change. Change of ES concentration with time in this part, this is called the steady state. So in the steady state, the ES by dt, the concentration of the change in concentration of ES with regards to time is 0 because it's a straight line. Getting my point? Okay, so the steady state is what they considered for. They're not considering this region, the pre-steady state, or they're not considering this region, the post-steady state. They are considering only this region to make the calculations. Okay, what is happening in the steady state? So in the steady state, the change of enzyme plus substrate concentration with time, the enzyme substrate complex concentration with time is 0. There's no change. After 20 minutes it's 0, after 20 minutes it's 10, after 30 minutes also it's 10, after 40 minutes also it is 10. Okay, it's essentially a straight line. So basically you have a region of pre-steady state, but then you have a region of steady state, the brown one. Okay, the brown one where the concentration of the ES with time is not changing. There's no change in the concentration of the ES with time. So when they say the steady state, we are talking about that region. Okay, the formation and the breakdown are equal. Essentially, dES by dt is equal to 0. The concentration of ES is not changing. Okay, the concentration of ES is not changing with time. You see the flat line. The concentration of ES is not changing with time. Okay, so why is it not changing? Because these two, the formation and the breakdown, are equal. Okay, at this point, some of it might break down, some of it might be newly formed, but there's a balance between those two, and essentially you don't see a change in the ES concentration. Okay, the ES concentration continue to remain the same, and that is the state we call the steady state. Okay, at steady state, the formation and the breakdown are equal. This steady state would only be temporary. Yeah, as you can see in the graph, only this part is steady state. The rest all is either going up or going down. Okay. Now, so at the steady state, you can put this equation as K1 ES is equal to, so the rate of formation is equal to rate of dissociation. Rate of formation is equal to rate of breakdown. Okay, that is when your ES is equal to, ES is remaining constant. So the ES, you know this formula. E plus S is forming ES and then E plus P. Okay, so this will remain constant only when this reaction and this reaction, so this, sorry, the forward reaction and both the reverse reaction and this reaction are actually balanced. Okay, in other words, let's say 100 molecules of E plus S are combining to form ES. And in this, let's say 25 molecules are breaking down and 25 molecules are being formed. So constantly 50 molecules of ES is maintained. So when the 25 molecules are being converted to product and 25 molecules are being converted to E plus S, 25 more molecules are actually combining, 50 more molecules of E plus S are combining back to form ES complex. So this number is constantly maintained. Okay, so whether it's the forward reaction or the reverse reaction, the rate of formation in the steady state is equal to the rate of dissociation or breakdown. So this reaction plus this reaction is equivalent to this reaction, because of which you are maintaining the constant ES. Okay, so that is what is shown here. K1, that is the rate of formation of ES, is equivalent to the rate of breakdown of ES. So it can be rate of breakdown of rate of breakdown to form product, or rate of breakdown to form E plus S again. So that's the reason we have both the constants here, K2 and K3. Okay, so that is the reason we have rate of breakdown is K2 plus K3 multiplied by the enzyme plus substrate complex concentration. Okay, that's the first part. Now, so from here on, it's just a rearrangement. So if you rearrange, you have this equation. Okay, now we can lump these constants. So all these constants can be lumped together to form, we can replace it with, these are all constants. So you can replace all these constants with a new constant called Km. So Km is basically K2 plus K3 by K1. Okay, then you get your equation Es is equal to E, the concentration of enzyme substrate complex is equal to this by, we are replacing this with Km. So by Km, and now Et, the total enzyme, so just understand this. In the tube, if you want to know the total enzyme, you have free enzyme plus you have enzyme combined with substrate. So if you add these two, the free enzyme concentration plus the enzyme which is actually involved in substrate complex, those two will give you the total enzyme. Okay, we cannot calculate the amount of ES, but we know the amount of free enzyme that you added in the beginning of the reaction. So Et is equal to E plus S. That is the total amount of enzyme equals to free, and that is bound to the substrate. So we'll just use this and then substitute Et. Okay, so Et minus Es is Es for E. So if you want to, so we know that Et is equal to the free enzyme concentration plus enzyme concentration. Now, if you want to get the equation for just E, we just have to subtract from the total. Okay, so Et is equal to E plus Es. So Et minus Es is free enzyme. So if you want the free enzyme, you just have to get it here. Simple. Then Es is equal to, so we'll just take this equation and put it wherever you need to address Es. Okay, sorry, free enzyme. Okay, we are replacing this with free enzyme. So we get this equation. Now solving for Es finally gives us this equation. You don't have to remember the equation. Okay, the reason why I'm explaining here is you have to understand the E total. Where is the E total coming from? Okay, it's a combination of your free enzyme plus enzyme that is bound to the substrate. Okay, so when you simplify the entire equation, it all boils down to this. It all boils down to this equation. Okay, so this equation is what we call the Michaelis-Menten equation. Okay, so this gives a quantitative relationship between the substrate concentration and the rate of the reaction. Okay, so this is the equation that you are supposed to remember. And so basically, if you know the substrate concentration, right, and the velocity of the reaction, you can calculate the rest. So you will see that there are many numericals that can be asked in this section, where you will be asked to calculate either the Km or the Vmax, right? V is the initial velocity. So when you're starting, okay, so this is your initial velocity, VO, and you're reaching your Vmax. Okay, so the velocity at any point, if you want to calculate the velocity at any point, we'll use the we'll use this equation. Okay.